Hey, minasan, konnichiwa, Zamurai Engineer desu. In this video, we are now going to discuss Module 7.3 of our second major topic. So this is about environmental loads. So again, let's start with the objective of the course. This course will provide you with fundamental concepts, principles, and theories on the structural analysis and design of steel elements in a structure. So we have the list of our major topics, and still we are in the last part of the load. So the next module will be module 8. So methods of design. So it's getting interesting. Okay, so let us complete this current module. So we are now on the number 3. So there are 3 types of load: dead loads, live loads, and environmental load. Okay. So environmental loads are caused by the environment in which a particular structure is located. So for buildings, environmental loads are caused by rain, snow, wind, temperature change, and earthquakes. Okay? Strictly speaking, environmental loads are live loads because they are changing the magnitude and location. Okay? But they are the result of what? Environment in which the structure is located. Okay? Even though they do vary with time, they are not caused by gravity nor operating condition, as is typical with other live loads. Okay. So there are several types of environmental loads. Number 1 is no load. So since we are using ASCE 7, that is American Society of Civil Engineers, this is applicable in their country. So therefore, they will consider their own climate, and one of which is the winter. So there are possibility of snow, but in our country that is impossible. So we'll skip that discussion. Okay, we will go directly to the number 2, which is rain. And rain, probably the most serious problem is panding. What do you mean by panding? If water on a flat roof accumulates faster than it runs off, okay, panding is a serious matter because if we have a large number of flat roof failures that occurs when they documented it in the United States. Okay, so there are a lot of failures due to panding. It has been claimed that almost 50% of lawsuit, meaning owners of the structure would take into court the design engineer. Okay, so being a design engineer is a serious matter. Okay, it has been claimed, no, that almost 50% of the lawsuits, okay, are concerned with roofing system. Okay, so panding is one of the most common subjects of such litigation. Okay? The best method of preventing panding is to have an appreciable slope of roof. What is the slope? 1/4 inch per foot. For every 1 foot, there is a 1/4 inch of slope. Okay. So together with good drainage facilities, scappers are sometimes used because of this. These are large holes or tubes in walls or parapets. What do you mean by parapets? You already know what is parapets. That enable water above a certain depth to quickly drain off the roof. So we will use what? Tubes, either plastic or what? Elastomeric tube. And, put them on the walls or parapets so that They are the provision for what? For water going off the roof. Okay. That is about rain. Number 3 is wind. So wind load. A survey of engineering literature for the past 150 years reveals many references to structural failures caused by wind and therefore typhoon. Okay, typhoon creates winds. Okay, perhaps the most infamous of these have been bridge failures. Tay Bridge in Scotland, 1879, 75 persons died. Tacoma Narrows Bridge in Tacoma, Washington, 1940. There have also been some disastrous building failures. Not only bridge, even building would fail due to wind during the same period, such as that of Union Carbide building in Toronto in 1958. Okay, 1958, there's a building. So those things have been studied. Their failure mechanism has been studied so that it could be put into the standard and code. Okay? It is important to realize that a large percentage of building failures due to wind have occurred during the erection of building. So recall, we had we reacted to a video of construction failure during construction, or in the concrete is still wet during pouring of concrete. Okay, so not only the load or the weight of the wet concrete, but also you have to consider the weight of the workers, and in addition, the wind. Okay, so because the wind is what could be horizontal, could be lateral. The wind could be lateral. And take note, the weakness of building and vertical structures are lateral loads. That is the weakness. Okay. So number 4 is about earthquake loads. Many areas of the world fall in earthquake territory, like in our country. We are actually in the ring of fire. We are member of the earthquake ring of fire. Okay? And in those areas, in our area, it is necessary to consider seismic forces in design for all types of structures. Through the centuries, there have been catastrophic failures of buildings, bridges, and other structures during earthquake. It has been estimated that as many as 50,000 people lost their lives in 1988 earthquake in Armenia. Okay, that is a disaster in Armenia. The 1989 Doña Preta and 1994 Northridge earthquakes in California. Okay, not to mention in those areas, in those countries, wherein they are member of earthquake ring of fire, like our country, like Japan, like Korea, like Taiwan. Those are in the ring of fire. Okay? Indonesia, I think Malaysia is also. Okay? So, those failures are catastrophic enough that many billions of dollars of property damages as well as considerable loss of life occurred. Okay, so the AISC manual does not provide detailed specification for designing structures subject to seismic load. So we are using AISC. We are also using our local code NSCP. There is a provision the NSCP, I think not thorough. There is not thorough provision, but there is a seismic provision in NSCP. Okay, NSCP 2015. Okay. But in such information is presented in other document like AISC, Seismic Design Manual. There is a specific document, okay, standalone document. So meaning the topic of seismic design is so great and so dangerous that it necessitates a document only for its load application, seismic application. So also references are given in ASCE 7 document, okay, about earthquake loads. Okay, so with that, we are on our last slide about challenge problem. Question number 50. What is the unit of measure of overhang? A, square meter, B, cubic meter, C, cubic meter per meter, D, cubic meter per kilometer. Again, what is the unit of measurement of overhang? A, square meter, B, cubic meter, C, cubic meter per meter, D, cubic meter per kilometer. So, this is Dr. EYPEI, Preaching Engineering Coordination Building.